Hey, everybody. Welcome back. And boy, we are moving right along. So we are closing in on the middle of the term. That should mean something coming up. But let's start. We're going to start introducing the concept of coordinate transformation. And coordinate transformations are fairly complex and they require you to be observant of your perspective, keep track of units, and know intentionally what type of transformation you're performing at each step. Typically, a coordinate transformation requires more than just one transformation. And we'll talk about the different types of transformations that we have. But for now, just to motivate the concept of transformations, let's go back to baby plane surveying 161. And if we have this coordinate, so let's consider a lateral view first. So we have an instrument set up and we have a point that we're measuring to. And so this is a lateral view first. So let's consider a lateral view. So we're standing on the ground looking at our measurement. And let's say we have our instrument here at A. And we have a hill, and we have point B up here. Then when we make our measurement, we are, change color here, shooting this line from A to B, or rather we're shooting the from the instrument to the height of the bipod. But for all intents and purposes, we're just saying we're measuring the ground, because we'll calculate that. And let's say that, let me label my axes here. So this is the zenith, or up direction. And then this is the horizontal plane, or the northing, easting plane. And if we diagram this out, we have, that's supposed to be orthogonal. We can get this horizontal distance here, can't we? If we have a zenith angle, so from our up axis or zenith axis, we have a zenith angle. And let's say our slope distance from A to B, or our slant range, is R. So R equals slant range. Or call that slope distance. Then we can get our horizontal distance. So horizontal distance, HD, equals R sine of the zenith angle. So our slope distance times the sine of our zenith angle gives us that horizontal distance. We've seen that a bunch of times. And we have our up. So from that distance there, our up value, equals, similarly, our slope distance times the cosine of our zenith angle. Right? So anytime we take a measurement, we have our zenith angle and we have our slope distance, and then we calculate our horizontal distance. And we want to remember that. So I'm going to write it up here. R, let's see, the horizontal distance which is in the northing easting plane, equals r sine zenith angle. Okay, so let's erase that. Now let's consider a top-down view of the same measurement. So top view. Same measurement, but we're just looking at it from a different perspective. And again, we have our A and our instrument setup. And let's say we have B here in the northeast quadrant. And this is the vector we're shooting. So we can label our angles. So this is our northing axis, this is our easting axis, and we know what this angle is. Excuse me. That is our azimuth. So alpha equals azimuth. And what is the length of our line? Well, that's our horizontal distance. So that is our r sine zenith angle. Just rehashing what we've done a million times. So we have a couple of values we're interested in when we do this, right? If those are right angles, we're projecting onto our easting. So this value here would be our delta easting, and this would be our delta n. And likewise down here, same values, delta E, change in the eastings, and this is our change in the northings. And from the diagram, before we go further, let me just say the delta E, we also know that as the departure. And the change in the northings we know as latitude, which is a horrible name, but that's what we call that. So we have our latitude and departure. And we know that delta E, or our departure, is equal to it's this value here, right? And that would be the sine of our azimuth. So that equals the sine of our azimuth times the hypotenuse. And our hypotenuse is r times the sine of the zenith angle. Just some baby trig here. And so if I rearrange that, then I have the departure equals r sine zenith angle sine azimuth. And our delta n, similarly, or our latitude, is equal to r sine zenith angle times the cosine of alpha. So just going back to plane surveying, reviewing how we work with angles before we jump off into coordinate transformations. And from the previous page or the previous drawing, we have our up, or u, delta u, our up, equals r times the cosine of the zenith angle. Okay, just review. Cool. And just to highlight, these would be our formulae that we use to get our northing value, our easting value, and our up value. And if we rearrange the terms and solve for our alpha or our azimuth and our zenith angle and our r, then we can go the other way, right? So we have alpha, our azimuth, equals the arctangent of the change in the eastings over the change in the northings, plus some constant to adjust for quadrant or for the quadrant, right? That would be either 360 or 180 or 0. And then we have the zenith angle is equal to the arc cosine of the change in the up value over r and finally r would be equal to the square root of the delta, the change in the easting squared plus the change in the northing squared plus the change in the up squared, right? Nothing new there, just a distance formula. So we're demonstrating that we can diagram the effect of a rotation and figure out the parts and pieces, and we can go back and forth. The same concept applies to coordinate transformations. Okay, I'm going to scoot this up, and I might come back to it. We'll see. Let's do an example. Examples are always good. So let's see. Given station low, at the ENU so easting, northing, and up coordinates, origin 0, 0, 0. So station low is at the origin. That would be our instrument station. The azimuth, alpha, and the zenith angle, and the slant range or slope distance, are as follows. We have alpha equals 240 degrees. Suppose we have a 240 degree azimuth. And our slope distance or slant range is 1,000 meters. And our zenith angle is equal to 92 degrees. So we're looking downhill, right? We need to find the easting, the northing, and the U, or the up. And we just apply those formulas. So let's apply the formulas. The formulae, excuse me. So we know delta E is equal to R sine of the zenith angle times the sine of our azimuth. And since our starting station is 0, that's just going to equal the easting. Our starting station, the easting of our starting station is 0 already. Then the change in the easting is just going to be the easting of the coordinate, right? And then delta N is going to be equal to r sine of the zenith angle times the cosine of the azimuth. And that, for the same reason, that's going to be our northing coordinate. And then our delta u equals, make that look like an n, just r times the cosine of the zenith angle. And since we're calling our instrument station 0, then that's just going to be our u coordinate, or our up coordinate. If we just plug our values from the example into those, we get E equals minus 865.498 meters. And our N is equal to minus 499.695 meters. And our up is equal to negative 34.899 meters. And as always, we want to check these values, just eyeball them to see if they make sense. Well, let's see. Our azimuth was 240 degrees, so we know we're going toward the southwest, or quadrant 3, which would have a negative easting, negative northing. We also know that with a zenith angle of 92 degrees, we should have a slightly downhill perspective, which means that our u value would be negative since we're starting at 0, right? And that's in fact what we have. So check. Those work. Just a quick example before we start complexifying this with transformations. Okay, so let's move on to transformations. We're gonna start looking at what's called a local horizontal coordinate system. Oops, it's not a G. You'll see local horizontal coordinate system referred to as LGH or ENU coordinates. So if you ever see coordinates that are in a northing and an easting and an elevation, those are LGH or ENU, local horizontal coordinate system coordinates. And let's see, we use LGH coordinates to integrate terrestrial and GNSS surveying. The transforming to the ENU coordinates allows us to apply typical Cartesian computations, whereas GNSS surveying is geodetic and requires the use of latitudes and longitudes and elevations. So or XYZ, or center Earth fixed coordinates. So it's usually most convenient to work in our northing, easting, and up coordinates. So to transform LGH coordinates to geocentric or lats and longs, I'll put or geodetic, coordinates. And vice versa, to go back and forth. We must go through the geocentric coordinates. The geocentric, and I'll just to differentiate from what I just said, the geocentric, Earth-centered, Earth-fixed coordinates. Which are the x, y, z. So to go from northing, easting, and up, we have to transform into x, y, z, and then to latitude, longitude, and height. And the same thing to go back. We have to go through those Earth-centered, Earth-fixed coordinates. Otherwise, we can't get there. And let me scoot this up a bit. So this means that if we start so let's say we have the ENU coordinates here. Now let me do this a little differently just to get us used to the verbiage. Let's say we have LGH, which are easting, our northing, and our up. Then we go to geocentric coordinates. Which are x, y, and z. And we have our geodetic. Which are, and I'll just to review, that's LBH, remember? And that's latitude and longitude and height. So if we start with one, we start in LGH, we have to convert to XYZ and then convert to latitude, longitude, height, and same going the other way. If we start with latitude, longitude, and height, we have to go through XYZ, and then we can get to our northings, eastings, and up. Okay? Let's see. In general, mathematically speaking, change color just for fun. Coordinate transformations, in the general mathematical sense, may include but are not limited to we can do, let me scoot this up. I'm going to leave that. A translation, which is just a linear movement along some vector. We can do a rotation, which rotates, we actually rotate our the reference frame axes. So a rotation. We can do scaling. We can scale our coordinates. Reflection, so we can reflect over any of the axes. We can do an inversion. And many others. So there are linear as well as nonlinear transformations. All those I listed are linear transformations. And we, in our world of cartography and surveying, we are mostly, if not entirely, focused on these three transformations: translation, rotation, and scaling. Hopefully that's no surprise. And within that, we are almost primarily concerned with these two. We don't, except in the case of converting from one unit to another, which we'll look at that when we get to 3D transformations. Scaling is something we don't do very often. So translation, rotation, and sometimes scaling. All right, let me bring in my shortcut diagram here. Okay, so just a basic set of axes. And let's see. So what color am I using now? I like that color. So just to get the idea, just to get our heads around what's happening with a rotation. So we're gonna look at rotations first, but in building our concept of translations and rotations, we often talk about we talk about transformations in terms of transforming coordinates or rotating and translating coordinates, scaling coordinates. What's really happening is we're not moving the coordinates of our points. We are introducing a new reference frame and then calculating what the coordinates of our points are in that new reference frame. That's an abstract idea. It's hard to imagine, but we're gonna build on this idea slowly. So to get the idea, let's start with a 2D rotation. And we're going to do all of our theoretical study in 2 dimensions. And then when we get to 3 dimensions, it's just sort of an expansion on the idea. All right, let's see. If we have 2 points, let's say we have a point Q and a point P up here somewhere. And then we have our vector between, right? So this is our vector. Now remember, we're just considering the basic mathematical sense. We're not really thinking as surveyors and cartographers right now. We're thinking just mathematically. So this would be my x-axis, this would be my y-axis, and I have an angle here. We'll call that alpha. I have my distance here. We'll call that r, the distance from Q to P, and we're just in 2 dimensions here. Remember, and then I can call this gamma. And we know that gamma equals 90 minus alpha. And same with alpha. Alpha equals 90 minus gamma, right? They add them together, they make a right angle. And let me just fill in the coordinates we're working with here. Q is at 0, 0, or our origin. And P is at some x, y. Good. Okay. Now, much like our plane surveying example, we are really interested in the change in our x and y values, right? So we have, that's a right angle, that's a right angle, and can say that's equal to alpha and that's equal to gamma for obvious reasons, right? We have our change in x up here. So change in x, which is the same as down here, right? Because we have parallel lines. So that equals r cos gamma, which also equals r sine alpha. Basic trig. Then our delta y, which is here, and that's the same as here, right? So delta y, I'll write it over here, delta y equals r sine gamma, which is equal to r times the cosine of alpha. Just getting our heads around these relationships, right? Okay, so we can certainly, I'm going to write this down, we can certainly impose and I'll put in parentheses or in quotes, prime, because we're going to use the prime notation, a prime reference frame by rotating the axes. And we'll just say about the origin, because we're not talking about translations yet. And all that means is, let's see, all that means is if I take my existing axes and rotate them, it's going to be, that's not very good. I guess I need to start up here. And let's say we rotate those axes by some amount theta. So that angle's theta, that angle is theta, because this is an orthogonal rotation, isn't it? All of the axes remain perpendicular. That's what we're going to look at for our rotation. So I'm going to take a second to pull in the next diagram. So let's see, scoot this off to the side and go find my other diagram that has a little more detail to it. And over here, like magic, I just found it. And I'll bigify that just so I can zoom in on this. I'm going to zoom in quite a bit because I really want to really want some space to draw here. Can't make it any bigger, I don't think. Yes, I can. So I'm just zooming in on this rectangle here. So here I have my original XY axis. So this is my y-axis. This is my x-axis. I've rotated the axes, and I'm going to say I rotated it by some angle theta. So when I do that, this becomes my x prime axis, and this is my y prime axis, which is why I was saying we can impose a prime reference frame. It's just terminology. Let's say originally my angle here, let's call that gamma. What I'm interested in is this angle. And what are we going to call that? I don't want to use alpha again. Let's just call it gamma minus alpha. It's the big angle gamma minus, or gamma minus theta. Sorry, not alpha. So that angle is gamma minus theta. I'm going to erase my arrow because I'm going to draw in here. Well, if we have that angle, recognize now that this is a right angle and this is a right angle, and that line is equal to that line is equal to that distance, or our delta x prime, right? And we have r here. Remember, our slope distance doesn't change when we rotate. You know, slope distance is the magnitude of a vector, so it's gonna stay the same. What we're interested in now is the length of that line and the length from the point to the new axis. So this one is our delta x prime, and this one is our delta, or sorry, that's our y prime. And I'll just say, so this distance here, that's our delta y prime. And this distance is our delta x prime, right? The change in x prime within our new rotated reference frame. There's a couple things we can note. So we would expect that this point, let's call it P, we can see that point would have the delta y prime would be less than the delta y, right? Because when I rotated my axes, that x-axis gets closer to the point. So if we have our slope distance and we have our angle, we can derive that delta x prime and delta y prime the same way that we did with the unrotated axis. And just from our plane surveying example at the beginning of the hour. So again, we're starting with our P having x and y coordinates, and we're transforming to some P prime, which is the same point, but with x prime and y prime as our coordinates in our new reference frame. Okay, let's see, where do we go from here? That's a lot of stuff on the drawing. So make sure that you're marking this down, and you should try to reproduce this diagram from memory eventually. So from inspection, I'll just put from inspection, if we just apply some trig definitions, then we have our delta x prime is equal to r cos gamma minus theta. And we know all those values, right? We know how much we're rotating. We know theta, how much we're rotating the frame by, and we know gamma because that was part of our initial observation. Okay, so, and then delta y prime, similarly, is equal to r sine gamma minus theta. Okay, cool. So now I have my, and since we started at 0, 0, in this case, that's going to equal the x prime of my p value, and that's going to equal the y prime of my p, I say that, my point. So I have my coordinates. From this we get or we have p prime is at x prime p y prime p. So same point, new reference frame, which means we have new coordinate representations. I think important to note, I'll just scoot this over a bit. All right. It is important to note that a counterclockwise rotation is positive, while a clockwise, and you know where I'm going with this, I'm sure, is negative. So in this case, we rotated counterclockwise, so theta is a positive angle change in our rotation, right? Okay, that's important to know because if we were to rotate our new reference frame such that x prime axis is, I'll say, south of the x-axis, then that would be a negative rotation, right? And we have that all the time. Anyway, so we have, these are the key characters right here that we're playing with. And we're going to play with those a little bit. Okay, so I'm going to move this out of the way. And let's start with what we know, what we just derived. So delta x, which is x to x prime, equals, what did I just have? So delta x, or x prime, is equal to r cos. And delta y, or y prime, is equal to r sine. Gamma minus theta. Now that's not a very convenient way of representing our function, right? What if we were to use trig identities? So we use a trig identity on gamma minus theta. So that our x prime becomes r, just applying a trig identity here, times the cosine of gamma times the cosine of theta plus the sine of gamma and the sine of theta. So just plugged in a trig identity here to get something to work with. And similarly, y prime is equal to r you know what? I'm not going to do that. Let's not muddy the water. Let's stick with our x prime, and then we'll just apply it to our y prime. So that equals, if I distribute the r in, I get r cos gamma cos theta plus r sine gamma sine. But some of these terms should look really familiar. This term here, if you look at your diagram, well, that's just my x value, right? My original x value. And the r sine theta is my original y coordinate, So in the original reference frame, I have my x and my y here, and I can rewrite this as x cos theta plus y sine theta. That's much nicer because now I have everything in terms of an original coordinate and the amount of rotation that we're giving our new reference frame. Very convenient, much more convenient than what we had above. So I can say similarly, we can do the same thing with the y. Y prime is equal to minus x sine theta plus y cos theta. All right, and those are the creatures we want to have in our notes to use for our rotated coordinate. Let's see here. X prime. There we go. So what do we do with that? Okay, so moving along, I'm going to get rid of my similarly word so I can kind of develop an idea. So transformations are pretty much what linear algebra is developed to address, okay? So what that means is, let's see, application of matrices and principles of linear algebra are essential tools to performing transformations. So if we look at, let's start with just what we have so far. If we look at our two formulae that we came up with, pick a good color, we have our x prime and our y prime here. We have our cos theta, sine theta as functions, and with that we have these functions. It kind of starts looking like we can form some matrices to get those results. And we want to do that because oftentimes we are performing transformations on hundreds of points. So we don't want to do those one by one. We want to have a way of performing the transformations all at once of all the coordinates. And that's what matrices do for us. The matrices that we want to use are, we have our x prime and our y prime. This together I'm going to call our x prime matrix. And to denote vectors in handwriting, I often put an extra line somewhere. So that means vector or matrix. So when you see that, like a letter with, or a number, or it's a letter or a symbol with a line striking through it in some angle, that's what I mean it's a vector or a matrix. So my x prime and my y prime is equal to the cos theta minus sine theta and sine theta. I should have this memorized. I do, just not very confident about it, I guess. And cos theta. And this is called the rotation matrix. or with a line through it, rotation matrix, and that's multiplied by my original coordinates, x and y, which I call the x matrix. We will call it that for this class. So x prime matrix, rotation matrix, and the x matrix. If we just apply the definition of matrix multiplication, what do we get? We get x prime equals x cos theta plus y sine theta, and y prime equals minus x sine theta plus y cos theta, which is exactly what we came up with before, right? That's our equations from above, our formulae from above, right there. X prime equals x cos theta plus y sine theta, yada, yada, yada. So that's just to demonstrate that it's a valid process to use matrices in place of individual equation, solving individual equations. So this is what we will use for our solution. So when we work with matrices, it is often, almost always, essential that we consider their cardinality. Cardinality is just the dimensions of the matrix. So for our R matrix, I'm going to erase that green line so I can write underneath it. Our R matrix is a 2 by 2 matrix, and our X matrix over here is a 2 by 1. So when we multiply that together, we should get a 2 by 1. It's the outsides, right? A 2-row, 1-column vector, which is in fact what we get. When you're building matrices, particularly when you're working in Excel, and we'll visit some of the matrix operations in Excel because that's going to become super helpful. We want to use Excel for matrix work. But when we get, pretty soon I'll go over some of those processes and like I said, the matrix routines. So anytime we apply a transformation, rotation matrix, and in other matrices, we'll do it all together to transform coordinates from one system to another. We call this process a reparameterization. We are giving the point new parameters, new coordinates. So we are reparameterizing, that's hard to say over and over, the coordinates. So it's called a reparameterization. Okay, let's do an example. A simple example. So given a point P, having X and Y coordinates, in some original system or reference frame. I need to start using that terminology. So in some, I'm going to say that, yeah, original reference frame, our set of axes along with the origin is a reference frame. Where my coordinates x, y are equal to, respectively, -5, 3. So given xy coordinates in one system of -5, 3, what are coordinates of x prime, y prime in a reference frame? I'm just going to say RF, reference frame, rotated clockwise. So a negative angle. Because clockwise negative, counterclockwise positive, by theta equals -135 degrees. So we're going to do that transformation of just the rotation. I'm going to leave my knowns up there so I can write them down. So solution. I have x, so my original givens, x equals -5, y equals 3, and theta equals -135 degrees. If I use my matrix definitions, I get, okay, well, I can come up with that. X prime, y prime equals cos of -135 degrees. Of course, we would, before we do the math, we have to convert that to radians, and minus sine of -135 degrees and sine of 135 degrees and cosine, oops, -135 degrees. That's my rotation matrix. So this is my x prime matrix. This is my r, or rotation matrix. And we multiply that by our original coordinates. So -5 and, no lie, it's not a fraction. -5 and 3. Super simple. If we perform that, we get our x prime equals our x prime, y prime, which is equal to 1.41. That's our new x coordinate in our rotated system, and -5.66. And I think I posted this on Canvas. And I think real quickly before we go, I'll show you how I did that in Excel. So here is a template. So I have my problem laid out. I have my x value, my original x coordinate, my original y coordinate, the theta value or rotation, which I've converted to decimal degrees and then radians. So here I have my x vector, and I'm going to fill in my rotation vector, and then their product is my solution, right? And since I have my nice handy formulae right there, my matrix formulae, I can just follow that, couldn't I? So let's see, in the 1, 1 position, that equals the cosine of theta and minus sine theta. And this should be sine theta. Go into the radians, referencing the cell. I'm not typing values in. Really important. If you type values in, you're missing precision. And then the cosine of theta. I'm just going to say that again because it's so important. Try not to type in values. 1, you're leaving yourself susceptible to fat finger errors, and 2, it takes a lot longer, and 3, you're not carrying all of the decimal place precision. All right. So now I just perform my matrix operation. Here's how we multiply matrices together. So if I need to, this is why we need to consider the cardinality of the matrix, because you have to know what to set up for your solution matrix ahead of time. So here I have so my x vector here is a 2 by 1, and my r is a 2 by 2. So if I multiply as it shows in my diagram down here, r times the x vector. So r is first. Remember, matrix multiplication is not commutative. So we have to do it in the right order. So I'm going to highlight, I'm going to end up with a 2 by 1 matrix. So I'm going to highlight a 2 by 1 matrix. I'm going to say equals. I want to multiply two matrices together. The function for that is mmult. So if I do that, and then I highlight the first matrix, which is my R matrix, and then comma, you're telling it what matrices you're passing in for the multiplication. My second matrix is the original X matrix of X and Y values, and I hit enter, and there we go. There's the solution, just that easy. That's why we want to work with matrices. It cleans up our process, it makes us less prone to errors, and it's just much faster and accurate. So that is, in a nutshell, two-dimensional reference frame rotation. Next time we'll look at translating, and then we'll put them together for a rotation and translation. Anyway, that's it. We're getting into some fun stuff, and we're going to let this one go for now. It's been a long session, and next time we'll look at translation. So have a great day. Thanks, and see you next time.